So our final speaker is Mike Gehm.
Thanks, everyone, and thank you for the invitation. So the title of my talk is Gigapixel. All the talks yesterday, today, I'm sure all the other talks in the conference, a lot of rigorous math, rigorous algorithmics, theoretical guarantees. There'll be none of that in this talk, and in fact, given that, perhaps a more appropriate title with apologies to the members of Monty Python is, and now for something completely different. So what I want to talk to you about today is a real-world system that generates sort of bleeding-edge high-dimensional data, and then hopefully connect that to sort of some of the themes and relevancies of this community. I'm going to talk to you about the AWARE program. It was formerly known as Mosaic. It's a 3-year, $20 million-ish DARPA program with the goal of generating economical, wide-field, high-resolution snapshot imaging. And I'll go through and talk about what I mean by each of those as we go along. The program itself is managed here at Duke by David Bradian, and the key insight of the program was his, and we'll talk about that in a little bit. It's a very large program. There's about 20 to 30 people that work on the project on a daily or near daily basis. Like I said, it's managed out of Duke, but there's many different subgroups. My role is to lead the image formation team at the University of Arizona, although I'm joining Duke in about 8 days. Again, many partners, corporate, other academic institutions, government, and so on. Last year we published a Nature paper on the result, and again you'll see the results in a little bit, and it was very well received, being selected as some of the top scientific stories of 2012 by a couple different popular organizations. So the goal, at the top, what I said, economical, wide-field, high-resolution snapshot imaging. So, we have to be cost competitive, not just dollars, but other system resources is a concept that's very familiar to this community. Wide field, that is, we want to be able to form imagery over very wide angles. High resolution, we want to see fine details. Snapshot, we want to capture the entire scene in an instant. So most large-scale image capture is done pan and scan. So picture, which rules out being able to deal with dynamic scenes. And so we want to actually have full snapshot capture over that entire high-resolution wide-field image. So these two, or these goals, create what I'm going to call the optical challenge and the data management challenge. So the optical challenge is, first of all, that physics sets a fundamental limit on the resolution of an optical system. So when you sample more finely than that, you're gaining more numbers, but you're not gaining more information, right? And so when you're pixel limited, your image has sort of this blocky nature, and perhaps then shrinking or increasing your sampling rate spatially would gain you more information. But of course, if you're optics limited, then really you're already sampling, at a higher rate than the underlying structure, and you're just wasting resources if you choose to boost your sampling. And so again, we want to have high resolution in a meaningful sense, not in a just we generate more numbers sense. So we want the optical resolution to be as high as possible. It turns out from information theoretical arguments combined with physics, you can show that there's a physical limit on the amount of information that you can pass through an optical aperture, and it's related to its size and the wavelength of the light that you're using. And it turns out to be hard to approach that limit with real physical systems when the input optics are large or when the angles involved are large. So the physics says, well, we should be able to resolve meaningful pixels along this line, but real systems, as they get bigger, they follow for a little while and then they tend to saturate. And so understanding why that's the case is going to be the key to trying to figure out how we're going to get past that challenge. Now, optical design, any optical surface introduces some type of error into how the system is propagating light. And that may be an intentional error. Maybe you can't afford to make the proper shape of that surface. Or maybe it's manufacturing tolerances, homogeneity of the material, anything like that. And so design, so you get sort of like these error surfaces and they're little potato chip kind of shapes. So optical system design is trying to pick the elements so that all these potato chips stack up and cancel and give you a pancake, okay? If you could get a perfectly flat, then you've achieved the ultimate limit of physics. But that should always be possible, but it may not be feasible. And so what you see here in a blurry picture is 22 years of Nikon lithographic lens development running up through 2004, so 9 years ago. The 2004 design contains 25 different pieces of glass. Each are aspherical surfaces, very difficult to manufacture. It's probably made out of, the optical equivalent of kryptonite. It's barely feasible on the scale of a semiconductor fab. And there have been 9 more years, probably 3 more process changes since then. So you can only imagine what the systems look like now. What David's insight, again, that launched the AWARE program, was that the idea is that you should focus on canceling these errors, these aberrations, locally rather than globally. And that leads to a new approach to optical design that he titled multi-scale optical design. So you have a shared input lens, and it's large because, again, the physics limits your resolution based on the size of that input optic. But then it's relayed to a parallel array of secondary optics, and they just cancel the aberrations locally instead of trying to cancel the aberrations over the entire field. So this makes it a simpler problem, so fewer surfaces are needed along any path to cancel. Further, one of the biggest aberrations is just the fact that when you're dealing with wide field, large angles, we can't approximate as if we're not really physically imaging from a plane to a plane. We're imaging from a curved surface to a curved surface, and you can't ignore that anymore as the angles get large. And so geometry just lets us actually put these secondary optics along a spherical surface in a way where it would be much more difficult, for example, to make a spherical detector array. Okay? So we can just eliminate that aberration completely by this method. And if this front optic has certain sufficient symmetries, then the optical design of each of these secondary optics becomes identical. And so you have economies of scale. And so it's just many of the same kind of optic. Now, this solution, using parallelization to avoid performance saturation, has proved itself in other arenas, computation being probably the most visible one. Supercomputers used to have ever more complicated vector processors, but there became a point where achieving the next step of performance became economically unfeasible. And so now, of course, we have massive parallelization of relatively simple components, and there have actually been several generations of that. Right now we're on to the GPU version of that, and each time it transitions to a new price performance curve. So the general concept is well tested. Okay, so that's the optical challenge and how we're going to address it. The data management challenge, high resolution means we're going to sample finely, wide field over a large range. So we're going to target gigapixel, that's 1 billion pixels. If we say 8-bit imagery, then that's 1 gigabyte per picture if we set aside compression issues for the moment, and you'll see why I think that's a reasonable thing to do. And then snapshot means doing it quickly, and if we're going to run at the frame rate of the sensors we have right now, that's 10 frames per second, so 10 gigabits per second or 10 gigabytes per second or 80 gigabits per second. So from a data perspective, that's what we're facing. So we're going to fill, again, setting compression aside for the moment, we're going to fill a terabyte hard drive in about 17 minutes with the system. And if we were so prosaic as to use only gigabit Ethernet lines, we would need an umbilical of 80 of them to carry the data. Okay. Now, there are absolutely technologies that you could address these things with. They may or may not be economical depending on the specific application, specific case you're dealing with, but it wouldn't really matter anyway because the data management challenge is also about display. A typical HD display is 2 megapixels. So you would need about 500 of them just to show somebody the 1 gigabyte image if you're going to show it to them in the traditional way. Now, tiled display walls exist, but generally only at a fraction of the 20 by 25 HD displays that you would need in order to show the gigapixel. So again, there's 4K displays now. There are technological steps, and you certainly could imagine building a tiled display of essentially arbitrary size if you were willing to spend the money. But again, we can boost this probably faster than that solution would scale. So we already have designs not for 1 gigapixel systems, but for 50 gigapixel systems, okay? And so we've already moved almost 2 orders of magnitude beyond the numbers on those previous slides. The point being that to effectively meet this data management challenge, we really have to stop and rethink what it means about interacting with images of this scale. There really has to be a whole new approach to the systems and to the resulting data. And we're not the first to come up with sort of this general idea, is that you want to view the camera as a data stream, that you allow one or more users to dip into and extract information out of. So for example, we might imagine multiple users, each with an HD display, which they can that is their own window into the data, which they can individually pan and zoom in real time. So user 1 might be zoomed out a little bit, observing this region. User 2 is trying to read that sign way back there. User N is spying on this person sitting in the chair on the patio. And really making the whole system independent of users and really having sort of this data stream, data store concept instead of the image as this monolithic platonic ideal. And then, of course, you can deliver and store full resolution snapshot or full resolution video as your bandwidth and other resources allow and based on application. Now, those two approaches, the optical solution and this data stream kind of solution, create a new challenge, which I'm going to call the image formation challenge. The acquired data is now a collection of individual micro camera images, this being some simulated ones. You see, number one, they're oriented in kind of weird ways because of how you have to lay them out on the sphere. Optics means that they get dark towards the edges. And we want to take that and we want to combine them into a seamless whole. And again, we're trying to do this at rate, so the goal is we need to be able to have a way to do this at the camera frame rate, and we should be able to handle these arbitrary zoom levels of multiple users. Traditional image stitching approaches don't really match this very well. So there's lots of techniques for if you go to the Grand Canyon and you stand there with your DSLR and picture, and you load them in and you get a big panorama of the scene. They tend to be relatively slow because they have to learn how the pictures are related to one another. They also tend to warp the image to make it more aesthetically pleasing when they're combined. This may be completely fine if all you're after is a pretty picture, but if you're trying to do something quantitative out of it, if you're going to measure scale or distance or what have you out of it, then perhaps you don't want things distorted to make them work better. And that many, not all, but many of the approaches tend to perform poorly on these micro camera images. Number one, because they tend to assume that you've taken a bunch of pictures with the exact same camera, and we have hundreds of their prescription is the same, but of course manufacturing tolerances mean they're all subtly different in a way that when you use your DSLR, it's all the same optics exactly each time. And then we have this fading to black and limited overlap, right? So the image is getting dim right where you are trying to figure out how it meets its neighbor. So the solution is, of course, to use this prior information that we have, right? In this multi-scale system, we have extremely precise information about how the micro camera images are related to one another, because after all, we've manufactured and bolted them into this dome structure. So for the most part, we should just assume that we know exactly where a pixel in the detector came from in space, so a model-based approach. Now, this won't be perfect, of course. We're going to have to learn periodically. Just thermal expansion of the dome is relevant on the scale of the images we're dealing with. But because that happens on slow timescales compared to the frame rate, we can amortize that learning and computational cost across longer periods of time and simply update the model periodically. And then by going to this model-based approach, we can take advantage of MapReduce, which is a distributed data processing approach, to give us very fast image stitching. So MapReduce, for those of you who aren't familiar, is an approach. It was popularized by Google, but many people have different implementations. And it breaks an algorithm up into two steps, each of which is massively parallelizable on its own. Not everything can be converted into a form like that, but we realized that model-based image stitching could be. And just briefly, if we think of, so this is like one of the detector arrays, and then we have hundreds of them, and each of the little squares is a pixel. We can think of the measurements on each pixel. We can turn it into a big, long list. Each list has an address, which says what micro camera it came from and what pixel it was, and then a payload that is basically the measurement of that pixel, knowledge about its gain and exposure, and stuff like that. So in the map step, we simply use geometry to say, well, this pixel came from this location in space, this, over there. And so all that does is change the address, okay? The payload stays the same, and that is independently parallelizable on each line in this vector, right? Each one can be mapped independently. Now we have multiple ones that end up in the same location in the image we're trying to synthesize. And so then the reduce step combines them all into a single payload value, okay? This process, the reduce step, is parallelizable over locations in the output. So on the input, we're parallelizable over detector pixels, and on the output, we're parallelizable over locations in the final synthesized image, each of which massively parallelizable. So map is just geometry. We know where everything is looking. What do we do for the reduce step? We use just a simple MLE method. We treat each pixel that we measure as a noise-corrupted measurement of the true irradiance in the scene at that location. And so a very simple form for the MLE. So it lets us compute the most probable likely irradiance at that point. And compared to some other ways that you might try to blend images from other multiple micro cameras, it number one flattens that roll off and brightness towards the edges and gives us really seamless intensity variation in the middle, and really does a great job. So AWARE-2 was the system, the prototype that we built that was reported on in the Nature paper. The design allows for up to 226 micro cameras around this central objective. We had populated 98 of them at the time of that paper. It would allow for 2 gigapixels, hence AWARE-2. It was 1 gigapixel as built, and so you see a drawing here relative to a soccer ball for scale. There's an actual picture of the device, and it observes over 120-degree field of view, circular field of view. If it was fully populated, we populated it so it was full width and about 50 degrees in height. Just some pictures of the drawing of the dome, the micro cameras and their control structure, insertion of the micro cameras into the dome. And so these are some of the images from the Nature paper. This is a shot that was done in downtown Durham. And you can see some zooms into the image, some architectural detail, somebody looking out the window wondering what's going on, someone standing on the top of the parking garage on the far side of the street. We aimed it up to see what we could see. So this is the full field of view of the sky that we were able to see with the camera and the constellations. This is what's shown on this slide. And then within each, we have some zooms showing Orion's belt and the Pleiades and other stuff. Again, no effort really to modify it for true astronomical viewing. We just laid it on its back and aimed up. Another neat thing is each micro camera has independent exposure and focus, and so we can synthesize extended depth of field and high dynamic range imagery very easily. So this is a shot, it's not projecting very well, but this is a shot out on the quad. The chapel was in extremely bright light. This side was in very, very dim light, and we can synthesize them together into a really nice HDR image. We're currently building AWARE-10. It's a 10 gigapixel system if it was fully populated. It's about 2x improvement in resolution. It's color, and it's smaller than the AWARE-2 system as we've gotten improved electronics, which were really the dominant volume factor. We've also, in the meantime, while building AWARE-10, have built what we're calling AWARE-2 retrofit, which is basically the AWARE-2 design with slightly improved optics and now color sensors. And so this is a shot that was taken in the Duke Gardens, a beautiful place to take pictures, and we can focus on an area and we can zoom in and we can see these people and we can zoom in. And again, you have this level of resolution across the entire field of view. Took it to Duke's graduation. So there's Melinda Gates up on the stage giving the speech, and again, imagery of everybody in the stands, all the way on the far side of the stadium. So just to wrap up, so what? What's the connection to you guys? First of all, it's a real-world, high-dimensional system that pretty much is living at the bleeding edge of bandwidth and storage availability. So definitely, many of the compressive sensing and related concepts that of this community are certainly relevant to taking these kinds of systems forward in the future. I think another really interesting thing to think about is how to approach this data stream view of the data, especially when we think about heterogeneous data. So right now, the system just runs at a frame rate, and so we take a picture at different instants in time, and there's memory buffers that live there, and really we just look at creating an image at any instant in time. But of course, we could use that memory, and we could intentionally change exposure times, and we actually do that a little bit for some of the HDR stuff. But we could change focus. We could imagine changing resolution potentially if there were various kinds of adaptive structures that were folded in. We could potentially imagine changing spectral band. So now, if we're going to go ahead and consider an image not as this static platonic thing, but as this data store, this data stream, what happens when you have a heterogeneous data store and data stream, and you want to be able to synthesize various kinds of information out of it? And again, I think that connects really strongly to a lot of the ideas that are being presented here this week. So with that, I'm going to end, and I'll be happy to answer any questions. But if everything has gone well, one of the cameras, out in front. Okay, so it is here. So one of the Gigapixel cameras is here. We want to take a group photo from the conference, and so there should be. It's out front. People will guide you out there, and again, unlike most group photos, don't worry about standing in a tight bunch. Just they'll let you know if you've gone way too far off and you're standing too far out of view, and we'll get a picture taken. But with that, I'll end and be happy to answer any questions. Thanks. All right. Well, smile.